So, Max, I was playing Sudoku on my phone last night, and I couldn't figure out this one puzzle. I started wondering if AI could do better.
Funny you should mention that. There's this AI approach called Hierarchical Reasoning Models that supposedly crushes Sudoku puzzles. But get this, some researchers found it can actually fail on puzzles with just one unknown cell left.
Wait, seriously? It can solve complex puzzles but fails on the simplest ones? That doesn't sound like reasoning at all.
Exactly, and that's what today's paper is all about.
Hey everyone, I'm Casey Park, a developer with a focus on structure and flow.
And I'm Max Stone, coming from a theoretical background with a focus on metrics and methodology.
Welcome to another episode of Totally Unprofessional Peer Review, where we break down the latest AI research papers so you don't have to read the fine print.
Today we're diving into a fascinating paper titled, Are Your Reasoning Models Reasoning or Guessing? A mechanistic analysis of hierarchical reasoning models.
This paper takes a hard look at hierarchical reasoning models, which had been making waves by outperforming large language model-based reasoners on various tasks.
The researchers conducted a mechanistic study and found some pretty surprising results. For one, these models can completely fail on extremely simple puzzles, which raises some serious questions about what's actually happening under the hood.
They also discovered something called grokking dynamics in the reasoning steps, where the model doesn't improve gradually, but instead has this critical moment where it suddenly gets the right answer.
And perhaps most interestingly, they found that these models might be guessing rather than truly reasoning through problems.
But here's the kicker. Once they understood this guessing behavior, they developed strategies to make those guesses better, boosting accuracy on extreme Sudoku puzzles from about 55% to nearly 97%.
So stick around as we unpack whether these so-called reasoning models are actually reasoning at all, or if we've just built really sophisticated guessing machines that happen to be right most of the time.
Let's dive into what makes these hierarchical reasoning models so interesting. The researchers found some really surprising patterns when they looked under the hood.
Right, and they identified three major surprising facts about how HRMs work. Let's take a look at this overview figure from the paper.
This figure really lays it out nicely. The first surprising finding is that these models can fail on extremely simple puzzles, which seems completely counterintuitive, right?
Absolutely counterintuitive. The researchers found that HRMs can actually fail on puzzles with just one unknown cell left to solve. Let me show you some examples they provided.
This is fascinating. In panel A, we see the model can solve very hard Sudoku puzzles, but panels B and C show that very simple ones cause it to overthink or even completely fail when there's only one cell left to solve.
The researchers attribute this to something called the violation of the fixed point property. Essentially, HRM is supposed to stop updating once it finds the right answer. That's the fixed point property. But in these simple cases, it keeps changing its mind even after finding the correct solution.
It's like when you overthink a simple question on a test. The answer is obvious, but you second guess yourself and end up getting it wrong.
That's a great analogy. The second surprising finding was what they called grokking dynamics in the reasoning steps. The model doesn't improve gradually. Instead, there's a critical moment where it suddenly gets the right answer.
Looking at this graph, the green lines represent successful solutions. What's interesting is that the loss doesn't decrease smoothly. There are these sudden drops where the model seems to have an aha moment.
Exactly. It's not gradually figuring things out. There's a critical reasoning step where it suddenly makes the leap to the correct answer. This isn't what we'd expect from true reasoning, which tends to be more incremental.
And the third surprising finding was about multiple fixed points. What does that mean exactly?
Let's look at this visualization from the paper to explain it.
So in this error landscape, we can see two distinct regions, one with the purple devil emoji and one with the yellow star. What are we looking at here?
This shows that there are multiple fixed points in the solution space, places where the model could settle. The yellow star represents the true solution, but the purple devil represents a false solution that can trap the model.
So the model might find this incorrect fixed point first, get stuck there for a while, and maybe never escape to find the true solution?
Exactly. The paper mentions that the model can linger for several segments before vaulting towards the true one, or sometimes it never escapes at all.
So when we put all these findings together, What does it tell us about how these models are actually working?
The researchers conclude that HRMs appear to be guessing rather than truly reasoning. They're making educated guesses about fixed points in the solution space, but they're not methodically working through problems the way humans do.
That's a pretty significant revelation. These models have been outperforming other approaches, but they're not actually reasoning in the way we might have thought.
Let's take another look at that overview figure to summarize what we've learned.
So we have failure on extremely simple puzzles due to violation of fixed points, recursion that's more like guessing, and fake attractors that act as pitfalls in the solution space.
And interestingly, once the researchers understood these patterns, they were able to develop strategies to make the guessing more effective, which we'll get into in our next section.
It's like they're saying, our model isn't reasoning the way we thought, but now that we know it's guessing, we can help it guess better.
That's a perfect summary, Casey. Understanding the true nature of how these models work, even if it's not what we expected, allows us to improve them in ways we couldn't before.
So, Max, let's dig deeper into what the researchers mean when they say these hierarchical reasoning models appear to be guessing rather than reasoning. That's a pretty bold claim.
It is bold, but they've built a compelling case. Let's look at this visualization that shows how HRM approaches solutions in the latent space.
These plots are fascinating. We're looking at different scenarios of how the model moves through its solution space, right?
Exactly. In panels A and C, we see what they call trivial cases. Either the model starts close to a good solution and easily finds it, or it completely fails to make progress. But the interesting parts are panels B and D, the non-trivial cases.
I see in panel B, it says, gets lost along the path. What's happening there?
That's showing how the model can get stuck near what the researchers call a false fixed point, essentially an incorrect solution that temporarily traps the model. In successful cases like panel B, it eventually escapes and finds the correct solution. But in panel D, it gets permanently trapped in the wrong solution.
So rather than methodically reasoning through the problem step by step, the model is more like taking a shot in the dark and seeing if it works.
That's a good way to put it. The paper explicitly states that HRM does not reason in the common sense way of approaching the solution gradually. Instead, it's more like making educated guesses and sticking with whatever fixed point it finds first.
Let's take a closer look at this error landscape visualization. This really helps illustrate the guessing behavior.
This is a fascinating visualization. On the right, we see two distinct regions in the solution space, one with the yellow star representing the correct solution, and one with the purple devil emoji representing an incorrect solution that can trap the model.
And that ridge between them is critical, right? The paper mentions that the model tends to get attracted to whichever fixed point is closest to its initial state.
Exactly. The researchers found that the latent state is consistently attracted to the fixed point closer to it. If the model initializes closer to the correct solution, it finds it quickly. But if it starts closer to the incorrect solution, it can get trapped there for a long time or even permanently.
That explains the guessing behavior. It's basically making its best guess based on where it starts, rather than systematically working through the problem.
Right, and the researchers even created a metric to understand this behavior better. They defined an error function that counts conflicts in Sudoku solutions, like having the same number appear twice in a row or column.
And what did they find with this metric?
They discovered that the false fixed points are actually shallow local minima of this error metric. Let's look at the visualization again.
So, along the path from the incorrect solution to the correct one, the error actually increases slightly before dropping to zero.
Exactly. That small increase creates a barrier that makes it hard for the model to escape once it's trapped in a false solution. It's similar to how gradient-based optimization can get stuck in local minima.
This really challenges our intuition about what these models are doing. We might think they're carefully reasoning through problems step by step, but they're actually more like sophisticated guessing machines.
Absolutely. And the researchers provide even more evidence for this guessing picture. They point out that techniques that give the model multiple chances to approach a problem from different starting points significantly improve performance.
Looking at this table, the accuracy improvements are pretty dramatic. The baseline HRM achieves 54.5% accuracy, but with all their augmentation techniques combined, they reach 96.
And they make an interesting analogy to human problem solving. If you're truly reasoning through a problem step by step, the number of attempts shouldn't matter much. But if you're guessing, having multiple tries dramatically increases your chances of success.
That's a great point. It's like the difference between solving a math problem by working through the steps versus just trying different answers until one works.
Let's go back to the overview figure to summarize what we've learned about HRM's guessing behavior.
So we have these three key insights: failure on extremely simple puzzles, recursion that's more like guessing, and fake attractors that act as pitfalls. And all of these point to the same conclusion that HRMs are guessing rather than reasoning.
That's right. And what's fascinating is that once the researchers understood this guessing behavior, they were able to develop strategies specifically designed to make the guessing more effective.
Which led to their augmented HRM with that impressive 97% accuracy on extreme Sudoku puzzles. It's like they're saying, our model is guessing, not reasoning, so let's help it make better guesses.
Exactly. They identified three strategies to improve guessing: data augmentation to improve the quality of guesses, input perturbation to increase the number of guesses by leveraging inference randomness, and model bootstrapping to scale the number of guesses by leveraging training randomness.
This really changes how we should think about these models. Instead of trying to make them reason better, maybe we should focus on helping them guess better.
That's the key insight. And it opens up new avenues for improving these models. If we accept that they're guessing rather than reasoning, we can focus on scaling the number and quality of guesses rather than trying to make the reasoning process more human-like.
It's a bit humbling, isn't it? We create these sophisticated neural architectures that outperform previous approaches, but at the end of the day, they're still just making educated guesses.
Humbling, but also exciting. Understanding the true nature of how these models work, even if it's not what we expected, allows us to improve them in ways we couldn't before. And that's exactly what we'll explore in our next section: how the researchers leverage this guessing insight to create their augmented HRM.
So now that we understand HRMs are essentially sophisticated guessing machines, let's talk about the really exciting part of this paper: how the researchers leverage this insight to dramatically improve performance.
Right. Once they realized that HRMs are guessing rather than reasoning, they developed three specific strategies to make those guesses more effective. Let's take another look at their overview figure.
I see they've labeled their improvement strategies at the bottom of each panel. We have data augmentation, input bootstrapping, and model bootstrapping. And look at that dramatic improvement on the right, from 55% to 97% accuracy.
Exactly. The researchers frame these as three ways to scale guesses. The first strategy is data augmentation, which they describe as scaling the quality of guesses.
Can you explain what they mean by data augmentation in this context?
Sure, remember how we discussed that HRMs can fail on extremely simple puzzles? The researchers found that by mixing samples of different complexity levels into the training data, they could restore what they call the fixed point properties of HRM.
So they're essentially training the model on a more diverse set of problems, including very simple ones, to prevent those weird failures we saw earlier.
Exactly. Let's look back at those failure cases to remind ourselves what we're trying to fix.
Right. Panel C shows how the model could completely fail when there was only one cell left to solve. By including more simple puzzles in training, they're teaching the model to handle these edge cases better.
And according to the paper, this data augmentation technique alone increased accuracy from 54.5% to 59.9%. More importantly, it eliminated those failures on simple puzzles that we discussed earlier.
That's a solid improvement, but still far from that impressive 97% they ultimately achieved. What were the other strategies?
The second strategy was what they called input perturbation, which is about scaling the number of guesses by leveraging inference randomness.
Inference randomness? But isn't the model's forward pass deterministic?
That's the interesting part. The researchers found they could create semantically equivalent input sequences with different formats. This creates a form of perturbation that gives the model multiple chances to approach the problem from different starting points.
I see. So instead of just giving the model one shot at solving a puzzle, they're giving it multiple attempts with slightly different input formats and then taking a vote among the successful attempts?
Exactly. And they point out that this is different from the cascade technique used in large language model evaluation. In LLMs, multiple passes naturally generate different outputs because next token prediction is randomized. But HRM is deterministic, so they had to deliberately create diversity in the inputs.
Let's look at the table showing how these different strategies improve performance.
This table is really telling. We can see that the baseline HRM achieves 54.5% accuracy. The plus relabel entry refers to this input perturbation technique, which boosts accuracy to 73.2%, a substantial improvement.
And what about the third strategy, model bootstrapping?
Model bootstrapping is about scaling the number of guesses by leveraging training randomness. The researchers used multiple train checkpoints of the same model architecture as different guessers.
So they're training multiple versions of the model with different random initializations and then combining their predictions?
That's right. Looking back at the table, we can see that the plus bootstrap approach achieves 64.7% accuracy on its own. And, when combined with data mixing, it reaches 82.9%.
This is a fascinating approach. Instead of trying to make the model reason better, they're embracing the fact that it's guessing and giving it more chances to guess correctly.
Exactly. And when they combine all three strategies, data augmentation, input perturbation, and model bootstrapping, they create what they call augmented HRM, which achieves an impressive 96.9% accuracy.
That's nearly perfect performance, and it all stems from their insight that the model is guessing rather than reasoning.
Let's revisit that error landscape visualization to understand why these strategies work so well.
Right, this shows how there are multiple fixed points in the solution space, the yellow star representing the correct solution and the purple devil emoji representing an incorrect solution.
Exactly. By giving the model multiple chances to approach the problem from different starting points, they increase the probability that at least one attempt will start closer to the correct solution and find it.
And the data augmentation helps ensure that the model doesn't get confused by simple cases or drift away from correct solutions it's already found.
That's right. It's a multi-pronged approach that addresses different aspects of the model's guessing behavior.
What I find particularly interesting is how the researchers turned what could have been seen as a weakness, the fact that these models are guessing rather than reasoning, into a strength by developing strategies specifically tailored to improve guessing.
That's a great point, Casey. It reminds me of how sometimes in science, understanding the true nature of a phenomenon, even if it's not what we expected, can lead to more effective practical applications.
Absolutely. And there's a broader lesson here for AI research. We often anthropomorphize these models and assume they're working in human-like ways, but careful analysis can reveal they're doing something quite different.
And the paper explicitly mentions that while their experiments focus on HRM, their analysis could extend to any recursive reasoner. They suggest that the qualitative taxonomy they provide could serve as a common vocabulary for this emerging class of models.
So the implications go beyond just Sudoku puzzles or HRMs specifically. This could inform how we approach a whole class of reasoning models.
Exactly, and it raises interesting philosophical questions about what we mean by reasoning in AI systems. If a model achieves nearly perfect accuracy by making educated guesses rather than step-by-step deduction, does it matter?
That's a fascinating question. From a practical standpoint, results matter, and 97% accuracy is impressive regardless of how it's achieved. But from a scientific standpoint, understanding the true mechanisms at work is crucial for further advancement.
And that's exactly what this paper contributes, both practical improvements and scientific insights. They've shown that by understanding the true nature of how these models work, we can develop more effective strategies for improving them.
To summarize this section, the researchers developed three strategies to improve HRM's guessing: data augmentation to improve the quality of guesses, input perturbation to increase the number of guesses through inference randomness, and model bootstrapping to scale guesses through training randomness.
And by combining all three strategies, they created augmented HRM, which achieved a remarkable 96.9% accuracy on extreme Sudoku puzzles, up from 54.5% for the baseline model. All by embracing and optimizing the model's guessing behavior rather than trying to force it to reason like humans do.
So there you have it. What we thought were sophisticated reasoning models turned out to be really good guessers. Kind of reminds me of that one professor in college who seemed brilliant but was just really confident in his educated guesses.
Absolutely. This paper really highlights how understanding the true mechanisms behind AI systems can lead to dramatic improvements. By embracing the guessing nature of HRMs rather than fighting it, the researchers achieved nearly perfect performance.
I think there's a lesson here for all of us in AI development. Sometimes what looks like a bug is actually a feature if you know how to leverage it properly.
Well put, Casey. And for our listeners, we hope this breakdown gave you some insights into the fascinating world of AI reasoning, or should I say AI guessing.
Thanks for joining us for another episode of Totally Unprofessional Peer Review. I'm Casey Park.
And I'm Max Stone. Remember, in the world of AI, it's not about reasoning versus guessing, it's about making your guesses so good that nobody can tell the difference.